In the last video, we saw Gauss's law for magnetism, which we found is just always equal to zero, so it's not terribly useful. But in this video, we're going to talk about Ampere's law, which does give us another way to calculate the magnetic field. And this is in chapter 31-3 of the textbook. All right, so to calculate, if you remember, Gauss's law for electricity was useful because we could use it to calculate the electric field when we had a lot of symmetry. So what we need is something similar for magnetic fields, and that relationship is known as Ampere's law. So Ampere's law is just written down here. So it's an integral, and the circle, remember, means a closed integral. So it's the magnetic field, B, dot product with some length element, dl. So this is a closed integral of B dot dl. So B around some closed loop, and that has to equal mu naught, which is our constant, permeability of free space, times the current going through that closed loop. So remember, this is a path integral since we're integrating over dl, and it's a closed path integral because of the little circle on the integral sign. So the idea is, the path integral of the magnetic field around a closed loop is proportional to the current through the area of that loop. So, and just like with Gauss's law, it's typically really only useful for currents and fields where you have a lot of symmetry. But when you do have a lot of symmetry, it's a lot easier than trying to calculate things with the Biot-Savart law. And again, just an aside here, so this is actually a special case of a more general relationship in vector calculus known as Stokes' theorem. All right, so how do you use Ampere's law? Well, just similar to what we had with using Gauss's law to calculate electric fields. So to begin with, you kind of have to know vaguely what the magnetic field lines look like. So you want to sketch the magnetic field lines, and just like for Gauss's law, we chose a Gaussian surface. Here we're going to choose an imaginary Amperian loop. And just like in Gauss's law, we're going to choose this loop in order to make this dot product and that integral we have to do easy. That's the whole key. So once you've done that, then it's just a matter you find the current that's going through the area of the loop. So you use the right-hand rule to get the direction or the sign of the current, and then you solve. So we'll do some examples of this in class, but just to show you what the results are for some special cases. So for a long straight wire, well, we've actually already done a long straight wire with Biot-Savart, but the magnitude of the field B is mu naught I over 2 pi r. So if you have a layered cylindrical wire, so again, you can divide it into outside the wire, where it just looks the same as what you have for a long straight wire, mu naught I over 2 pi r. If you're inside the conducting piece, so that's the orange bit here, and you get an expression like this, has to do with the difference in radii of the currents. And then finally, if you're inside the insulator, so that's this purple part on the inside here, there is no current, so the field is zero.